Here we are reviewing the artificial neural network based functions, and in this training we train reverse outputs, which are row C, row T, H and D in this sequence, starting with row C here. When you train row C, we are using a 9 inputs, and the rest of the other one cannot be used as input parameters because they are placed with row T in output layer. Therefore, we have here 9 by 1 matrix size for input parameters. And again, the bias is matching the neurons for input layer, actually for every hidden layer, so that we know automatically that bias should have 40 by 1 sizes when we have a 40 neurons. The 40 neurons are implemented in this function, ANN based functions, whereas we have 4 layers right there, so that the matrix size should be then 40 by 9, because the 9 and 9 cancel each right here, so that you end up here 40 by 1 matrix when you multiply W and input parameters, so that they are consistent in size as 40 by 1 for the first layer. And don't forget, we have to put them in the activation function here. So okay, so we have used 10H activation function here, because the 10H activation function here default activation function in MATLAB. We have used a MATLAB toolbox to train this big data sets. To train big data sets, use a MATLAB toolbox. So MATLAB toolbox is very powerful, and as long as you understand the concept, and we don't have to go and make codings. So we just use and call for MATLAB toolbox, and very conveniently training and predicting all these outputs right there. So where we have used a 10H as default activation functions, and again we go and continue the same process up to the output layer. So we're going to do that probably 4 or 5 times, depends on how many layers you have here. Let's take a look at a artificial neural networks here. The neural values on first hidden layers right there, this one is calculated using a weight matrices that connects the input layer to the first layer. As you see over here, this is the weight matrices that connect the input layers to the first hidden layer. If you take a look at the first hidden layers over there, and this is very simple to understand. And also the bias is added right there, 1 bias for each neurons in here, let's put this way, one here, so on and so forth, for the entire first hidden layers. And the ANN based functions are also is provided right here. This is very interesting functions. If you see here, I indicated red color that represents the matrix expressions you see here, and right there you have a weight matrices and input parameters and biases, and you also don't forget to put them into the activation function as indicated here as well. And this represent the matrix formulation as you see over there. If you go and second hidden layer, you're gonna have a similar expressions right there. But this is a matrix that represents and connecting the first layer, hidden layer, to the second hidden layers. That's the differences. Now you move from here to over here, and you're taking a look at a second hidden layer and what's going on over there. There also I express them in functions, neural network based functions. Here, blue part also represents this matrices. The red part was calculated from the first layer, and it's gonna be used as a input parameter for the next layer, which is second hidden layer, and multiply that by the weight matrices right there that connects the first hidden layer to second hidden layer. So this is very systematic and very easy to follow, and you go and repeat all the way to the last layer. Maybe last layer is upper layer, isn't it? So the last layer, and calculates the output parameters that you are looking for from these neural networks. And so when you have a 3 hidden layers and 1 outputs, then you have a 3 plus 1 matrix formulations. So we have a first, second, third hidden layer, and we have output layer. Assume that way. Then we're going to have a 1 expression, matrix expression, 2, 3, and 4. Okay, this is how you're going to end up with the matrix formulations. So if you have n layers plus 1 upper layer, then you're going to have a n plus 1 matrix formulations. It's very easy to follow. The same thing can be said to this ANN based functions. You're going to have a n plus 1 type of pair for the ANNs, which has a n hidden layers and 1 upper layer. Now here you have a 4 layers, so you're going to have a 4 matrices plus 1 matrices, including the matrix for the upper layer. So this is very easy to follow how many matrices you need, how many pairs of ANN based function you have right there. So this is what happens when you go over to the next output parameters, which is rho RT. This is rho RT, hard to see. This is rho RC. Starting with the rho RC, and this is rho RT. And what you're going to have here are 5 layers and 40 neurons. And the number of neurons don't change. So that you have here now 10 by 1, and this is 40 by 10. And that's exactly similar to what you see over there. And again here 10 by 1. Why 10 by 1? Because we use rho RC as a input index, feature index to predict rho RT in here, right here in these functions. So we have 10 by 1 and we have 40 by 10. Therefore we have 40 by 1 bias matrix, and we go next, which is H. Now we increase the number of input to 11, and your matrix becomes 11, and so on and so forth. And these are only showing the expression functions for the first hidden layer. Then you're going to see the second hidden layer by modifying the functions in the same way that I showed a few minutes ago. As you see here, as you see here, as you see here. So what that means is your neural values that you calculate from first layer is used as input for the next layer, which is right there, multiplied by W2 and put them in the activation function as you see over there. Now this is a weight matrix, and bias matrices connecting input layer and the first hidden layer. So the connecting input layer and the first hidden layer is shown here. The first hidden layer here and the input layer here. So the weights you're looking at, this is the weight you're looking at, connects input layer to the first hidden layer. So we are looking at the very first matrix formulation as I explained. So again we are looking at a D. D has 9 input parameters, which is right here, 9 by 1, 4 input parameters, and you're going to have automatically 40 by 1 bias matrices should be provided. Therefore, your weight matrix dimension should be 40 by 9, where you cancel these two, so that you end up with a 40 by 1 matrices, which is consistent with the sizes of B, right? And your neurons, this is a neurons at first hidden layer, it is 40 by 1. It's again the first hidden layers, and we printed the reduced numbers right there. I can put all 40 and 9 something. So we have here. I include all 9 here. 1, 2, 3, 4, 5, 6, 7, and 9. That's possible, but I just reduce and hide some numbers over there. But this is 40. This dimension is 40, and this is the numbers, which is representing weights. So all these weights are obtained by the training. Again, we use a MATLAB toolbox simply to get this weight matrices. They are now correct one, even though the matrix started with random numbers at the first epoch, but after how many iterations we have performed to train D? We're talking D. This one, D here. Yes, this is D. So we went to see 15,595, and the best epoch was found at 15,095 iterations. This is amazing, very lengthy process to come up with a correct weights. Okay, so this weights start with random numbers at the first epoch, and after 15,095, after lengthy processes, you end up with very correct weights to be able to use in design. I'll show that sometime later. And this is a weight matrix. I'm going to take a look at a annual bias, one more weight matrix that connects the last hidden layer and the upper layer. Okay, last hidden layer and the upper layer. How many upper layer we have? We have a one upper layer, which is B in this case, which is D. I'm sorry, which is D in this case. This is D, and this is a weight, and this is a bias. This is not a parameters. This is a neural parameters. This is design parameters, which is D right there. So D should be 1 by 1. Only D is calculated at the end of the neural network. So this is D. Okay, and we have here one by one bias matrices, and we have neuron value of previous hidden layer. This is previous hidden layer. Previous hidden layer, which is fifth, isn't it? Because we know that the D has 5 hidden layers. If you see over here, we have here 5 hidden layers are used to predict D. So there's no doubt that we have here 41 by 1 neural values for 5th hidden layer, and therefore your weight matrix should be 1 by 40. Why 1 by 40? You have to cancel that to come up with a 1 by 1 matrix to be able to predict D as a 1 by 1 matrix, just single number, I mean. And there you have here 1 by 40 weight matrices from the training, and you have 1 by 1 bias matrices, and this all matches the matrix dimensions, then verifies your neural networks and training were successfully performed, and you end up with a full matrix for bias and weight matrices, and this is very nice to see. And we're ready to go over the design of the doubly reinforced concrete beam after we repeat same thing for all reverse output, and based on the TS1 sequence where you see the training sequence right here, or TS2 sequence where you have a sequence, see right there. Okay, and we're going to continue.